In our last video, we talked about exponential growth, and we derived an equation for exponential growth based on a very simple assumption, which is that the number of infected people is proportional to the infection rate. But as we saw, it got out of hand for larger numbers because the model wasn't entirely accurate. So we're going to try to fix that. First, let's write down the equation for exponential growth and see how we can fix it. So we have dn over dt equals constant times n, and you should check out my previous video if just for background. So we saw that this was wrong for larger values of n because the infection rate, which is dn over dt, couldn't be large for very large values of n, specifically large compared to the population size. So we need to add some sort of limiting factor here that makes dn over dt very small when n gets close to the population size. And we can actually do that very easily with a bit of math. What we're going to do is we're going to multiply by a factor. And this factor is going to be 1 minus n over p, where p is the population size. Just for reference, n is the number of infected people, and p is the total population. Now this equation satisfies all our conditions. When n is very small, we still want exponential growth. That was accurate for small values of n. And you can see here, p is very big. P is 8 billion for our world. And when n is very small, it's going to be like 2 over 8 billion. It's going to be negligible, almost 0. So this whole section over here is just going to be about 1. And if it's 1, well, we're left with our original equation for exponential growth, c times n, which is valid. Now we want the opposite extreme when n is very large. Well, we don't want that. Nobody wants that. But we want to check if it works. So when n is very large, n over p is almost 1. Let's say almost everyone in the world is infected. That means that this factor gets very close to 1. So 1 minus the factor is almost 0. So the change in n is something multiplied by 0. Anything multiplied by 0 is 0. So when n is very large, the change is going to be very small. That's great. This satisfies all of our conditions. So we could actually solve this mathematically as well. I'm not going to bore you with the math, and I'll just do it. And there we go. We integrated some stuff, and we get this ugly looking equation over here, but it's actually not that bad, and I'll explain to you what it means. So p over here is the population, n is the number of infected people. We already know that. This big fraction over here is just a fraction telling us what fraction of the population is infected. So we're going to have n naught over p minus n naught. You can see this appears twice. This fraction is a fraction specifying the number is a fraction like it gets bigger when the initial number of people infected gets bigger. So it's a fraction telling you kind of what percent of the population was infected at the beginning. And e to the ct is familiar. This is the exponential function. It's the thing that grows really fast. When t is small, e to the ct is going to be very small, right? When t is small, because we have to remember n naught over p minus n naught is a very small fraction. In our example, at least, n naught was 1, p is 8 billion, and it's going to be 1 over 8 billion, which is negligibly small unless e to the ct is big, right? So when e to the ct is small, this whole thing can be pretty much ignored when compared to 1. And we're going to get our original exponential function, yes. And now the thing is, with this fraction, it gives out the right values for large values of t, because e to the ct grows very fast, and we can see that after just a month or so, it's going to reach the order of magnitude of billions. And then we have this on the top and bottom. So this whole thing, I'm gonna box it or show it to you. This whole thing appears on the top and the bottom. So no matter how big it is, when it's very, very big, it's going to approach 1. This fraction is going to approach 1 because you're going to have a very big number over 1 plus a very big number. And that's good because that approaches our population size. It's probably best if I graph it so you guys can see what it looks like. visually. Normally it helps to have a visual of what you're looking for. So again, we're going to have n and t. This time, we're going to start off with one person infected. It's going to increase very fast at first as well, just like the exponential function, but then it's actually going to start slowing down. And it's going to approach this asymptote over here. And this asymptote is precisely the population size. And you can see that from this equation over here. When t is very large, we just saw that it approaches the population size. Now it's great. Now we have a model that's pretty good. That's, well, not pretty good. It's still very far off. But it's better than the previous one, at least. At least now there's some sort of limiting factor. And it gets closer to the right answer because now we can adjust things about this model to make it closer to what an actual pandemic looks like in society. This is one of the worst case scenarios where everyone gets infected. Obviously, this is not true either. And the thing about this that is not true is that it takes some erroneous assumptions as well. For example, it assumes there's no doctors in the world. It assumes that after you're infected, you go around running around like you're the Mongols or something. So, and also it assumes that nobody recovers from this disease. So these are all wrong assumptions that we can account for and fix later. But nevertheless, they were assumptions that helped us develop some sort of model, at least, for how something grows. And that's it for this video. This is called logistic growth. And next video, we're going to be getting a better model, as you might have predicted from the trend of these.